This video is for F2, conservation of momentum. In a closed system, the total momentum never changes. And a closed system is one where there are no externally applied forces to the bodies within the system. Imagine a closed system of four masses moving around as I've pictured here. The total momentum of this system is the momenta of each of these masses added together. Remember, momentum is a vector, and so these momenta are vectors. They have direction. And the diagram I've drawn here is in 2 dimensions, so each of these momenta has an x component and a y component. This total momentum of my system will never change, unless there's an externally applied force, in which case it's not a closed system. This means that if bodies are allowed to collide or interact in some way, then the total momentum before that interaction will equal the total momentum after that interaction. For now, let's keep things simple and imagine a one-dimensional picture where we have two masses that are travelling towards each other and are going to collide. The initial momentum can be written like this, but we must be careful because u1 and u2 are vectors. Exam boards will insist that you write a minus sign between these two because the velocity 1 is in the opposite direction to velocity 2. And as they are in opposite directions, when you add those vectors in one dimension, you subtract the magnitudes of those vectors. Now that momentum will equal the momentum after the collision. And if v1 or v2 is negative at the end, then that means it's travelling in the opposite direction. It's often easier when problem solving to instead add our momenta and decide which direction is positive. So let's say that the direction to the right is the positive direction, in which case the negative part is here on our left-hand side of our equation. That's where the negative number is. After the collision, depending on the masses, it could be that V1 is negative. So I will emphasize again, the equation I'm highlighting here is absolutely correct as long as U1, U2, V1 and V2 are vectors. But in your examination, especially if you're substituting numbers, you must make sure you put a minus sign in so the examiner knows you appreciate the direction of those velocities. Now for a closed system, that equation I've written is always correct. There are 3 situations when you might be asked to apply the conservation of momentum. That is for elastic collisions, inelastic collisions, and explosions. In elastic collisions, there is no loss of kinetic energy. That is to say that the total kinetic energy before a collision is equal to the total kinetic energy afterwards. Kinetic energy is half multiplied by the mass of a body multiplied by the square of the speed of the body. So the equation becomes this. For elastic collisions, we have simultaneous equations, with the top equation with the green box around it correct, and also the equation at the bottom of the screen correct. You will not have to deal with those in your A-level physics. Usually for elastic collisions there'll be one unknown for the equation in the green box, and you'll have to rearrange that equation and find what that value is. Now, whilst energy is always conserved in a closed system, in inelastic collisions kinetic energy is not conserved. Kinetic energy can be transferred to a different store, such as thermal energy. In A-level mathematics you will learn about coefficient of restitution. In A-level physics it doesn't go that far. So inelastic collisions you'll encounter in A-level physics will be perfectly inelastic. And that is to say that the minimum amount of kinetic energy is conserved, bad choice of words, in order for the momentum to still be conserved. In other words, there's the maximum possible loss of kinetic energy. To put it simply, that happens when two bodies collide and stick together. So the final velocity of each body is the same. This can be simplified with the equation I've written here. In explosions, kinetic energy increases, but total energy in the system remains constant. And that usually means that chemical energy or elastic potential energy has been transferred to the kinetic energy store. The most common type of question with explosions will be a situation where the initial velocity is 0 for both bodies. They're in one place, and then after the explosion they're moving apart. Because the initial situation, the two bodies are stationary, the equation can be rewritten like this at the bottom of the screen. The majority of the questions you will encounter for conservation of momentum will be in one dimension. But if you do meet conservation of momentum in 2 dimensions, don't panic, just handle each direction separately. The momentum is conserved independently in the x direction as in the y direction, and indeed in the z direction. So here's an example question. 2 vehicles collide and stick together. Vehicle 1 travelling at 25 meters per second and vehicle 2 travelling at 10 meters per second in the same direction as vehicle 1. Vehicle 1 has twice the mass of vehicle 2. What is the final speed of the 2 vehicles? The first thing we do is write down the conservation of momentum equation. We then recognise that because the 2 vehicles stick together, they have the same final velocity. The mass of vehicle 1 is twice the mass of vehicle 2, so we can substitute this into the equation on the left. The equation now can be shown with an m2 in each term, so if we divide through by m2, every m2 cancels and we are left with the equation here. The right-hand side can be simplified, like this. And now all we have to do is substitute in our numbers. Let's first of all get v as the subject. There, now let's substitute in our numbers. So 2 times 25 plus 10 divided by 3, which equals 20 meters per second. And that's how you answer questions about conservation of momentum.